And the universe size u is 2 to the w, this 2 to the w minus 1 is 2 to the w minus 1. Okay. And we also assume that pointers fit in a word. Okay. So for the last assumption, if you have a data structure that's storing n items, presumably your data structure is using at least n space to even remember what the items were, right? So we know that space is at least n. Okay. And if a pointer fits in a word, well, a pointer is what? An address into our space. So w should be at least log of the space, which we just said is at least log n. Okay, so we're always going to assume that our word size w is at least log n. Okay. And what I'm going to show you today and on Thursday are two different predecessor data structures that get different bounds. One is going to be better when w is small, like closer to log n. One is going to be better when w is very large. So two data structures. So one is the, it's called the Van, well, that's lowercase, Van M. de Boas trees. This is from what year? Sometime in the 70s. So I'll frequently put the conference or journal name in the year. So this is for the scribes. And this is due to Van M. de Boas. And if you Google it, you'll find a reference. So please put a reference in the scribe notes. And what this gets is update. This is dynamic, so it supports updates. Update and query are both going to be log w time. Okay. And the second thing that I'm going to cover, and it's, and we're going to show also that, well, let me say something else. The unfortunate thing, though, is going to be that the space is going to be u. And I like linear space, independent of the universe size. Right? Imagine if you have a 64-bit machine, u is 2 to the 64. So I don't want to use 2 to the 64 space ever. And we'll see that this can be made theta n with randomization. And we'll also see a related data structure called Y-fast trees, tries, which get the same bounds. Okay. And this is due to Willard in IPL 83. So originally, Van M. de Boas in his paper didn't get linear space. But the move from U space to linear space is going to turn out to be pretty simple. And the second data structure we're going to see So this is the one that can be made dynamic, but I'm only going to present the static version in class. Otherwise, it gets too complicated. These are fusion trees. Okay, and this is due to Fredman and Willard. I believe in JCSS 93. Okay. And these support query in time log base W of n. Okay. And it's also linear space. So already this beats binary search trees, right? If W is at least log n, remember log base W of n is the same thing as log n over log W. So this is never going to be more than log n over log n. Okay. But of course, we could choose, if we know W, I mean, we know the machine that we're coding on. If we know W, we can choose the better of fusion trees and, let's say, Van M. Du Bois trees or YFAS trees. So that implies that we can achieve the min of log W and log base W of n, right? And the min of this is, if we want to maximize this expression, we'll do it when these two things are equal, which means log W equals log n over log W, which means log n is the square of log W. Okay. So this will be always at most square root log n. Okay. Okay, good. And I mentioned that this can be made dynamic. So in particular, that means you can sort in time n times the square root of log n. Okay. Things that I won't cover in this class. This implies with dynamic fusion trees, O of n root log n sorting. Okay. Question?
So for sorting, why do you need dynamic?
So there's going to be there's an issue which I haven't discussed, which is the pre-processing time to actually create the data structure. Right. So in the dynamic case, when you start with an empty data structure, that doesn't come into play. But with the static case, we're going to spend polynomial time to actually create this this fusion tree, and that's going to be bad for sorting. Any other questions? Okay. So you could ask, is n root log n the best sorting algorithm in this model? And you can actually get faster sorting. Okay. So you can get O of n log n deterministic. This is due to Hahn in Stock 2002. You can also get O of n square root log n, expected time randomized. This is due to Hahn and Thorup in Fox of 2002, which is about 5 months later. And it's an open question whether or not you can get a linear time sorting algorithm in this model. So it's possible. There's nothing saying that you can't do it. Okay. And let me go back to the word RAM model before I actually present the Van Em de Boas data structure. Okay, so I mentioned we can do more than just compare. So what can we do? So in word RAM, assume that given x, y fitting in a word, we can do basically all the things that you can do in, say, C. So you can do integer arithmetic, so plus, minus, divide, times, minus. And this is integer division, so it rounds down. Okay. You can also do bitwise negation, XOR, OR, and can't write and properly. Okay. And you can also do bit shifting with some fixed constant, or with each other. Or okay, yeah.
So the result of the calculation, like in multiplication, that
Yeah.
also have to fit in a word, or that can be worked out?
So we'll assume that for multiplication, it fits in 2 words. So the upper bits will be in the second word. Yeah. Okay. Any other questions? Though I think it's also accurate to say, we don't need to, I think, make that assumption. There could be integer overflow, in which case we'll get the overflow of the correct answer, but you can simulate multiplying bigger numbers using in the word RAM anyway. So maybe I'll leave that as an exercise. You might need to use a couple words yourself when you do the arithmetic. Okay. So we can do these in constant time. So just out of curiosity, who's seen Van Em de Boas trees? So who's seen fusion trees? Okay. So okay, good. Just making sure I'm not teaching you something you've seen. Okay, so we're doing Van Em de Boas. Okay. So the basic idea is, well, I guess you guessed that we're going to do something with fudging with bits, because we can't just do comparisons. The basic idea is some kind of divide and conquer. Okay. So so VEB trees will be defined recursively. So what a VEB tree will look like, and it'll be parameterized by the universe size. So let's say this is on a universe, say, of size U. It will look like, if I open up what it looks like inside of that data structure, it'll have square root U VEB data structures each on a universe of size square root u. And there will also be a top one of size on universes of size square root u. Okay. And separately, we'll also store one extra element, which is the minimum element in the data structure. And I'm going to say more. Okay. So, let's say you're using some object-oriented programming language, and you wanted to declare the fields that your VEB data structure has. So, the fields of VEB, let's say on a size u universe, you would have an array of size root u, a root u size array. Let's call this thing V. V is our VEB data structure. You'd have v dot cluster 0 up until v dot cluster square root u minus 1. And this is a VEB square root u data structure. What I mean is the elements in here are numbers between 0 and square root u minus 1. We'll also store the max. Maybe I'll say that too. Let's say we also store the max. I'm going to write that down here. We also have a v dot summary is a VEB square root u instance as well. And v dot min, v dot max are integers in the range from 0 up to u minus 1. Okay. Any questions? I haven't actually told you how you insert into this data. This will be a dynamic data structure. So I haven't told you how you query, and I haven't told you how you insert. So let's see that. Okay. So say we have an item that we want to have living in this data structure. So x is some integer. Okay. So we can write x in binary. And we can divide x into the the leftmost half of the bits and the rightmost half of the bits. And we call this c, and we call this I. So let's write x as ci. Okay. And notice that these numbers c and I are in the range from 0 up to root u minus 1. Right? Okay. So we're basically writing x in base root u. And the idea behind Van M. de Boas trees is that we will store if x lives in the data structure, then we will store the number I in the cth cluster. Okay? In this picture. Okay. So now tell me, if given what I just said, how would you say do a query for the predecessor of x? And hopefully people agree that you can extract c and I each in constant time just by bitwise anding and shifting. Okay. Okay, so how would you search for the predecessor of x in this recursive data structure as I've defined it? I guess I didn't tell you what the summary does. Let me tell you what the summary does too. So I told you that I'll insert I into the cth cluster. Okay. Also, if the cth cluster happened to be empty when I did the insertion, I'll also insert C itself into the summary. Okay. So the summary keeps track of which clusters are non-empty. That's the point of the summary. Okay, so now how would you do a predecessor? Yeah.
You have your query element, extract C of the query element, find look in that cluster, like do the recursive query on that cluster, and if it's the lowest element in that cluster, you find the next lowest non-empty cluster in the summary and look at the maximum.
Okay, yeah. So what you said works. There's one recursive call you could save,
Okay.
right? Which is, we store the min explicitly.
Yes. Okay.
So so let me just repeat what you said, but using that fact. Are you here for advanced algorithms?
Yeah.
Oh, okay. Well, yeah.
Don't worry about that.
Okay, so here is the idea, right? So I can extract C and I each in constant time using shifts and masking with bitwise and. And then what I do is I look in the cth cluster, okay? And I look at the minimum element in the cth cluster. If I'm bigger than it, then I know my predecessor lives in the same cluster as me, and I can just recursively do a predecessor in that cluster, a predecessor on I in that cluster. If there is no minimum element, if that cluster happened to be empty, or maybe I'm bigger than the min, bigger than or equal to the min, then I know my predecessor is not in my cluster. He's in the largest cluster before me that's non-empty. And how do I find that? I find that by doing a predecessor on C in the summary. And then I return the max inside of that cluster. Okay? Okay, good. I don't need to recurse on that cluster. I just return the max. Good. So let me write that down. So so predecessor takes as input v as well as this x, which I write as ci. Okay. And I say the first if is if x is bigger than v dot max, so if x is bigger than everything in my data structure, I just return v dot max. Okay. Otherwise, I look at the cth cluster of v, and I check its min and compare its min to me. Also v dot cluster c dot min is less than x, then I'll just recurse. otherwise, what? I have to look in the summary for the predecessor cluster. So C prime will be my predecessor cluster. And then I return the maximum element in that cluster. Okay. Okay, so the next thing is the insertion algorithm. Okay. So the first thing is, we're going to see why in a moment, but I'm going to treat the minimum element as being special. It's only going, so the minimum element will be stored in this minimum field. Where are my fields? The minimum element will be stored in the minimum field, but I won't also store it in its appropriate cluster. Okay. So it could be that the v.min is some non-empty value, and everything else in the data structure is empty. So if v is empty, I'm going to say v.min gets assigned to x, and then I'll return.